Afternoon, everybody. Stage B. I'd like to welcome Kev Sheldrake, who will talk about cracking HiTag2 crypto.
Hello. So it's been quite an exciting day. I spoke. Hi, Graham. I spoke at about 1:30 in the other tent when I was very, very sober, and all I can say is I've been sitting in the sun drinking ever since. So I am going to go through this quickly, and I'm only going to be able to talk about some of the content that's normally in this talk because of the limited opportunities to, the limited lengths that we have to speak at. But if you do have any interest, or you want to ask questions, or you want to just like come and hang out, I will be outside the bar. Buy me a beer. You can ask anything you like, and I will demonstrate every crack that I don't happen to have in this talk then. But you have to buy me a beer to get to that point. I'm going to talk about HiTag2 crypto. This is me. I work in cyber. I do interesting things with crypto and RFID. So the first question is, why do we copy RFID tags at 125 kilohertz? So for those that don't know, RFID exists in two, low frequency is like 125 kilohertz, high frequency is 13.56 megahertz, and very high frequency is 866 megahertz or 433 megahertz, depending on where you live. So why do we care about 125 kilohertz RFID, which are basically quite old as a technology, and they're going out of fashion, they're disappearing? It's because they're used to protect things that are far more valuable than the amount of money it costs to break it. And most 125 kilohertz RFID tags are rubbish, but the ones I'm talking about are less rubbish, but they're still rubbish, unfortunately. They're also used to protect the, to implement the car immobilizer in most cars. I've since been contacted from giving these talks by Audi and Nissan because apparently they're using that technology. Who knows? So normal RFID at 125 kilohertz looks like this. It transmits a single page of data over and over and over again whenever it's powered up. And at the start of that single page of data is a synchronization pattern, which the reader and the tag both know. And when the reader detects that synchronization pattern, it reads whatever bits come afterwards and turns that into a number. And that is the number they then use to make access control decisions. Clearly, you can copy these easily by just emanating a field at 125K and seeing what number comes out, write it down, and then program that to another tag, right? So they're trivial to break. At an electromagnetic sort of spectrum basis, this is kind of how it looks. The reader emanates the field. The tag has no battery. It absorbs its power from the field, and then it damps that field on and off in a pattern to signal information to the reader. And if the reader wants to transmit information to the tag, such as I want you to write this page with a particular value, then it damps the field in a particular way as well. The way that they damp the field is one of these types of keying modulations, and possibly encoded with Manchester biphase or not, as the case may be. I'm not going to talk about this anymore. The many months that I spent looking at this technology, I had to learn a lot of this stuff, and none of this is interesting to the crypto world. Yes, it's very interesting if you care about radio, and I did at the start of this project. So I'll quite happily talk about it, but honestly, the crypto is much more interesting, so we're going to skip this bit. So if we wanted to secure 125 kilohertz RFID, what we'd want is two-way comms, and we'd want some sort of authentication and then some sort of encryption such that you couldn't replay the comms and you couldn't copy the tags easily. That's kind of the goal. So I'm going to talk about HiTag2, which is one of these. Not that it makes any difference because that's the standard ISO card, but it's HiTag2, which is the technology, I say, probably in your car immobilizer, and possibly in the tags that let you into the building that you work in password mode and in crypto mode. And you might note from the contents, I'll talk about password mode very small amount of time, and I'll talk about crypto mode a large amount of time. That's because password mode is rubbish, as we're about to see. So what I won't be talking about is everything else, and specifically cars, but come and talk to me later if you want to know more. So it all started with an academic paper. Basically, we had a job which involved breaking into buildings by copying RFID tags, And one of my colleagues said, I think this academic paper it says a lot about the sort of system that we're looking at breaking. Would you like to have a look at it, and could you implement the stuff that they're talking about? And this is the academic paper. It's called Gone in 360 Seconds, Hijacking with HiTag2 by Fedor Garcia and Balash. I've met Flavio Garcia. He's a lovely man, very Italian. And the stuff they did is awesome. It's very, very clever mathematics. It's very hard to understand. They wrote code to implement 3 attacks in this paper when they produced the paper in 2012, and then never released their code. And for 5 years, no one had written that code, and people were asking for it on the RFID forums. And that's why we decided that we should write that code and release it, which is what we've kind of done. So HiTag2, what does the HiTag2 tag kind of look like? Well, it kind of looks like this if you drop it into acetone and then magnify it with a child's microscope. So for the sake of a pound for the acetone perhaps, and £30 for the microscope, and £700 for a decent SLR, you can get photos like this as well. And in the bottom right one, it does actually say HT2, which means HiTag2. If you looked closer, it would say Micron, which are the people who originally made it and stamped the silicon that Philips then bought, that NXP was rebranded to. But this is largely pointless. It's just fun. What a HiTag2 really looks like is this. This is logically what it looks like. There's 8 pages of 32 bits of data. So the first page is the UID. That is stamped into it in the factory and is not changeable. You can buy Chinese HiTag2 tags where you can change the page 0 data, but typically the vast majority in the world that you will see, you can't. And it doesn't matter because it's not important to the crypto. Pages 1, 2, and 3 contain secrets, which is why they're red. Pages 4 to 7 contain user data, such as this user's ID within the system, which the system then makes access control decisions over. So whether you're in password or crypto mode, the whole system resides on shared secrets. Now, it would be lovely if there was enough processing power to do asymmetric crypto in these kind of things, but there's not, because at 125 kilohertz, it just isn't the power to do these kind of things. So therefore, you have to do symmetric encryption. And if you do symmetric encryption, then you basically have to share the secrets. And what that really means in practice is that if you have a system with 1,000 doors and 10,000 users with tags that can open those doors, or a subset of those doors, then every door reader and every tag has the same secret within it. And you only have to compromise one bit of that system to access the secret, and then you can compromise the rest of the system really, really quickly. So this is kind of fundamentally bad as security goes in terms of access control. When you move into the worlds of 13.56 megs and you look at DESFire, EV2s and things like that, these problems don't really exist in this kind of form, and things are much, much better. But if you were to look at another crypto system, whatever it happens to be, and you found that kind of signature, then your alarm bell should ring. You should start to think, well, I could probably just compromise a tiny bit of this, and then I could own the whole thing. And to compromise a tiny bit of it really means I just need to steal something and take it apart, which is kind of what I did. So password mode. I'll talk about password mode really quickly. So the reader in password mode constantly emanates the binary pattern 11000 using pulse width modulation of the field. And when a tag enters the field and powers up, it sees that and it responds with its UID value from page 0. The reader then sends page 1 in clear, which is the system password, and the tag responds with the tag password, page 3 in clear. And then the reader talks to it in clear and the tag responds in clear, right? Now, so if you can eavesdrop on that, you can get all the passwords, right? So password mode is awful. We're not going to talk about that anymore in this talk. Crypto mode, however, starts with the same thing. So basically your system can be either in password mode or crypto mode. It can't be a hybrid. So in crypto mode, it's emanating 11000, the same pattern in pulse width modulation. And the tag responds with its UID in clear because there's no established creds at that point. But at that point, things are seeded, the encryption system exists, and the reader sends the encrypted nonce, and the encrypted challenge response value to the tag. The tag responds with an encrypted page 3. The reader can then send encrypted commands, and the tag can then respond with encrypted responses, right? So the whole thing is much more encrypted. This is kind of how it looks in terms of what data is needed where. The reader has the key and the nonce and receives the UID from the tag, and from that it seeds it and randomizes its PRNG. Equally, the tag has the same data. It uses that to seed and randomize its PRNG, and then both PRNGs end up in exactly the same position, exactly the same state. This is a key thing that I keep forgetting to say when I give this talk, but if the PRNGs are at exactly the same position, seeded and randomized with the same data, they will then chuck out the same randomized binary stream. Okay, and that's important because that's how you use them in a stream cipher. So, for example, if the reader wanted to encrypt some data to send to the tag, it would say, I want to encrypt, I don't know, 32 bits of data. I'll get 32 bits of randomness from my PRNG and XOR that with my data and send it to the tag. And the tag could go to its PRNG and go, I want 32 bits of data. And it would get the same 32 bits that the reader got because they're in the same state. It can then XOR that with the data it's received, and that will give it back the plain text. This is a key thing to how this attack, or the first attack that I'm going to talk about, works. So stream ciphers, if you aren't aware, are basically XORing with a pad. Stream ciphers are rubbish, they're awful, please don't use them. Don't take any of this as examples of ways you should build systems. But the amateur cryptographer sat next to you will tell you that the only secure cipher in the world is a one-time pad, and it's not, because it has no integrity protection. So I can own the one-time pad with certain caveats. Anyway, let's talk about the HiTag2 PRNG and encryption. So the HiTag2 PRNG is based on a linear feedback shift register that is 48 bits wide, and it is initially seeded with the 32-bit UID, which is from the page 0 of the tag, and the first 16 bits of the key, which obviously the tag and the reader both know. Next up, the reader invents a nonce, a 32-bit value, which could be properly random. It should be properly random. And it XORs that with the upper 32 bits of the key, and then it pushes that in one bit at a time into the LFSR as it extracts bits of output from the LFSR. Those bits it extracts from the LFSR, it uses to encrypt the nonce by XORing each bit of the nonce with the next bit of the output from the LFSR, which creates an encrypted nonce, which it then sends to the tag. The tag can then do the same thing. So it gets the output from its PRNG, XORs that with the upper 32 bits of the key, and XORs that with the 32 bits of the encrypted nonce. Of course, you can't do that from the outset because you don't have 32 bits of output from the PRNG. So you only have one bit of output at this particular moment in time because you only have one state that you know. So you take the first bit of output from your LFSR PRNG, XOR that with the 16th bit of the key, the first bit of the upper half of the key, and XOR that with the first bit of the encrypted nonce, which will decrypt that bit of the nonce XORed with the key, which is the next value that you need to push into the LFSR. So it then pushes that value in, which shifts the whole LFSR by one bit, at which point you can then generate the next bit of output, XOR that with the next bit of the key, XOR that with the next bit of the encrypted nonce to decrypt it, XORed with the key, which happens to be the value that you then push in. It's a really neat scheme, and when you've done it all, both the reader and the tag end up in exactly the same state. It's not secure, but I really like it. It's kind of cool, all right? It's like how to decrypt and seed your LFSR at the same time. It's like it's a neat thing. It's just not secure, right? For really complicated mathematical reasons that I can't even go into in this talk, but it's not secure. I will say, if you're interested, by the time I get to the end of this, I'll be pointing you at a GitHub where you can find all the other code, right? Other attacks that I've implemented from the academic papers. I mean, as I say, none of this is my invention. I've literally just coded up what they've said in maths and turned it into C, right? But other attacks use that fact to completely break the crypto really, really quickly. So it is worth bearing in mind. Anyway, so after the tag and the reader have got to that state, they have no more randomization or seeding information. They need to continually be able to shift through the LFSR and invent new bits that get pushed in as the thing shifts? Well, they use the feedback function L to generate the new bit. So it takes the LFSR state and generates one bit. And so when you encrypt, it kind of looks like this. Literally, you get output from the PRNG, XOR that with your data, and that produces encrypted data. I say it's a stream cipher. And the receiver can do exactly the same thing. The function L will produce exactly the same stream of bits based on the state that you started with, so it gets the same PRNG output. It can XOR that with the encrypted data that you've just received, and that will return it back to the plain text, and then you have the plain text data. The feedback function, if you care, looks like this. It is literally the XOR of 16 bits of the LFSR. So the LFSR is 48 bits wide. It takes 16 of those, XORs them all together, and that produces one bit of output. That is the new bit that gets shifted in. So if you don't know the entire LFSR state, there's a good chance you don't know the new bit that's getting pushed in. And the output of the LFSR, the PRNG, is not just the bit that falls off the right-hand side when you push it through. It's actually generated with a filter function. And that filter function is based on functions A, B, and C in this kind of arrangement. So functions A and B take 4 bits each from the LFSR and produce 1 bit of output. And those 5 single bits of output get pushed into function C, and that produces 1 bit of output, and that is your output. Each of functions A, B, and C are biased 50-50, which means if you don't know the input, you can't predict the output with any confidence either way. There is a 50% chance of getting a 1, a 50% chance of getting a 0. So looking at that, you'd think, that seems pretty cool, pretty secure, right? You know, because how could you guess this sort of stuff? Well, you look at some of the other attacks, those academics are quite clever. There's ways of breaking these things that I've implemented. You can read the C to understand how it works. So if we go back to my slide about how crypto mode worked, it sends the start auth, the tag responds with its UID, the reader sends the encrypted nonce, the reader sends the encrypted challenge response value, the tag responds with its encrypted password, and then the reader sends encrypted commands and the tag responds with the encrypted responses. So let's look at HiTag2 commands. HiTag2 command is only 5 bits long. The first 2 bits determine which command it is from read page, write page, or halt. And the following 3 bits determine which page of data we care about. So if we're trying to read a page or write a page, those 3 bits will tell you which page we care about. Read page inverted is essentially read page, but every bit that comes back is inverted. Fair enough. And halt turns the tag off until it leaves the RF field and comes back into it again. And the reason that's there, or a use case of where that's used, I should say, is in Las Vegas casinos, where every chip has one of these tags inside it, and the entire table is circulated by an RFID field, and therefore they can track every tag being on the table or not on the table. So when you set your field up and you kind of go start auth, the first or fastest or loudest tag will respond, and that'll be the one that the field hears, and then the field will then communicate with that one. All the other tags will ignore the communications because they don't meet the integrity checks that I'll come to in a minute. And when it's finished talking to that tag, it then sends the halt command, which shuts that tag down while it's still in the field. And then it does a start auth, and the next loudest or closest or noisiest tag will respond, and it will talk to that one, and it can cycle through all the tags within the field. So you can talk to multiple tags within a single field using this, because you can halt the loudest ones first, if you see what I mean. So if you want to use this in a really hostile environment, take it to Las Vegas. Apparently they use this stuff. Now, so HiTag2 commands are 5 bits long, but in actual fact, in a practical level, when you send them, they're actually 10 bits long. So it's the first 5 bits followed by that 5 bits inverted. So a 0 goes to a 1, 1 goes to a 0, right? So 1, 0, 1, 1, 1, inverted becomes 0, 1, 0, 0, 0. And so an actual command, the minimum size it can really be is 10 bits. This provides integrity checking. Like if you're trying to read a tag, or maybe you're trying to write a page, and the write page command gets corrupted and you accidentally write to the wrong page, that could be quite devastating in some kind of industrial situation. So With this, the same bit would have to be like corrupted in the first 5 bits and the second 5 bits for it to pass the integrity check. It basically checks that each block needs to be the inverse of the preceding block, right? But extended wise, you can have as many of these blocks as you like, as long as every block is the inverse of the preceding block. So you could have 20 blocks as long as it goes normal inverse, normal inverse, normal inverse, normal inverse, which apparently adds to the integrity. What it actually does is creates a hole through which we can attack the system. So let's talk about attacks. And we're going to talk only about the first attack. But the academic paper from 2012 has 3 attacks in it. I've implemented all 3. I'm going to talk about the first one. Flavio Garcia then went on and wrote another paper in 2016, which has a new attack, which is much faster. Vincent Imler produced a GPU-based attack that took 11 hours, brute force, in 2012. And last year, Thales and the French government produced an optimized version that would work on Amazon using multiple GPUs and multiple hosts. And then I just got word only last week that one of the other authors of the first paper produced a new paper last year that can attack the whole thing in like 30 seconds or something. Some incredible another attack that I now need to go and read about just for completeness, you know, to satisfy my OCD. But basically, there's lots of ways of attacking these things. I'm going to talk about one. The one I'm going to talk about is the nonce replay and length extension for key stream recovery attack, which is a long sentence, but it's really straightforward. Honestly, we're going to replay a nonce several times, and using that, we're going to extend the amount of key stream that we can recover until we get enough key stream that we can then break the crypto. So what you might have noticed when we were looking at how these things work was that all the entropy comes from the reader in the form of the nonce. So if you have one tag, one HiTag2 tag, it has a single UID on it, and every time you present that to a field, you'll get the same UID. So if you stick with one tag, that UID is not going to change. The key on it, equally, is not going to change because it's the same key on the entire system, and that is, again, fixed. So nothing on the tag is generating any entropy. When you put it in the field of the reader takes that and seeds it, and it generates a nonce, and then it encrypts that nonce and sends it to the tag. And the nonce, together with the key and the UID, is what seeds the PRNG, right? So the only entropy is that nonce. So if we have a device such as one of these, perhaps, and our fiddler, and we eavesdrop on the communications between a tag and the reader, we could steal an encrypted nonce and an encrypted challenge response value from that one handshake. And then in our little back smoky room somewhere else, we could then replay that nonce and challenge response value over and over and over again to the tag. And every time we replay it, the tag would reset to the exact same position each time, the same PRNG position, because all the entropy comes from that nonce. And the challenge response value just proves that the nonce is a valid nonce, essentially, properly encrypted. So if you remember that this is the position that the reader and the tag got into after they were seeded and randomized, then we could create this in emulated reader and pretend to be a real reader. Because all the reader has to provide is the start auth command, which we know from the spec, the encrypted nonce we captured, the encrypted challenge response value we captured, and then it will get back the encrypted page 3 from the tag, at which point the tag will be in a particular state, and if we do it again, it will be in exactly the same state. And however many thousand times we do this, it will be in the same state each time. So, for example, if we gave it the encrypted nonce of 4A85B2DF, we might expect that PRNG output of 01011001110101001, for example. And each time we initialize the tag with that same nonce, we would get that same PRNG output, which is what is being used to encrypt the stream of data. It's kind of really important to understand how the nonce replay works, which is why I labor that point like so strongly. So the way we're going to attack this is we're going to try and find the read page 0 command, right? Because we know the answer to page 0. Page 0 is the UID, right? So we already know what answer we should get, even though it will be encrypted. But if you're working from the position of something you already know, attacking it is a lot easier. Now, if an encrypted command is 10 bits long, because a basic command has to be at least 10 bits long, and then it gets encrypted to random noise, essentially, then there's 1,024 possibilities. And out of that, there's 16 correct answers, of only of which one will be the read page 0 command. So we could search and search and search. When you send an invalid command, you get this unencrypted error response of F402889C. And it has to be unencrypted because the idea is that the reason it's gone wrong in the normal use case is because something's gone wrong with the encryption. If something's gone wrong with the encryption, you can't expect the tag to be able to decrypt your encrypted error response. Therefore, it has to send an unencrypted error response value, and it's always the same number. So we can use that as a canary in order to work out, or an oracle, in order to work out whether we're sending the right commands or not. So like one way of attacking this would be to, we're actually going to bit flip, but so one way of attacking this would be to send 1,024 or up to 1,024 encrypted commands, one after another, cycle through them until we get something that isn't the error response, right? Which would be the dumb brute force approach to doing this. So I'm going to have a drink because it's been at least half an hour. I should do me till the demo. But this would be dumb, right? Yeah, you can obviously see why this would be pointless. But the reason it's pointless is because if we imagine what an encrypted command would look like, we know that if the encrypted command is EFGHI as individual bits, we know that F decrypts to 1 and K decrypts to 0 because CM0 has to be a 1 for a read page command, and K has to be the encryption, the inverse of that. Or the decryption of K has to be the inverse of the decryption of F. So we know those sort of parameters. We know what they must decrypt to. But equally, we know that the decryption of E, G, H, and I must be the inverse of the decryption of J, L, M, and N, right? And we don't know what the pad is that we're dealing with, but we are using the same pad each time. So what we do know is that we don't have to care what J, L, M, and N actually decrypt to. They could decrypt to a random bit pattern. We can search E, G, H, and I to find something that decrypts to the same as that. And that takes 4 whole bits out of our search space, which reduces our space to 2 to the 6 rather than 2 to the 10, which means our chances of finding something will be, we'll probably need to send 32 actual requests before we hit an actual success, as opposed to 64. So we've halved the amount of work we need to do. Honestly, it's cool. It's crypto cool, you know. So we find one valid read command, right? Because basically we just do that until one of them comes back with a different response to the unencrypted error, right? Now we have one valid read command. Now what we're going to do, rather than search for all the others, we're going to bit flip that to find all the others, because then we don't have to actually do any transmission over the RF, right? It's much quicker. So if the one we found is EFGHIJKLMN, then we could take that and imagine that decrypts to read page 4 inverted as the actual plain text. Well, the first half and the second half, when they're decrypted, must be the inverse of each other. Because it's a stream cipher, if you flip a bit in the encrypted version, it flips the same bit in the plain text version, which is where all the integrity and the insecurity of one pad ciphers kind of fall down, right? So we could flip the first bit, E, for example, in this example. And in this example, it would flip it from a read inverted to a read command. But if it was originally a read command, it would flip it to a read inverted command. Okay, so but in order to maintain the integrity, we also have to flip the same bit in the inverted half. So bit 6 also has to be flipped. But because of the nature of stream ciphers, if we flip the bit in the ciphertext, we flip the same bit in the plaintext, we can do the same thing on bit 6 as well. So if we flip bit 0, we also have to flip bit, if we flip bit 1, we also have to flip bit 6. And that will flip it from a read to a read inverted, or a read inverted to a read. But either way, what we end up with is a valid read command. Equally, we could flip a bit in the page bits. So if we had read inverted page 4 and we flipped bit 5, it would flip it to read inverted page 5, as long as we also flip bit 10 to maintain the integrity by flipping the same bit in the second half of the command. That's really neat. So basically, given one actual read command that works in the encrypted form, we can flip it around until we get all 16 by basically just building a table. It's really trivial. And then what we can do is try every one of them out. One of them must be read page 0, like not inverted. And that's the one we're looking for. So what we'll do is we'd go around a loop of trying each of the 16 possibilities. Every time we'll reset the tag back to the same position with the same nonce to the same point of the PRNG, and we'll test our guess. And if it's right, we'll store the key stream that comes back. And if it's wrong, we'll just go around the loop and try another one. And each time we will reinitialize the tag because we're working from the same position of that PRNG. Because we're using an emulated reader that's replaying the same nonce, that if you replay the same nonce, you get the same key stream back. I repeat this enough times to hope that it gets boring, so you just understand what I'm saying at this point, because I'm always fearful that I'm saying stuff and people are kind of going, but why? Why does that work? It's like, it's not actually that hard, honestly. So if we try our guess, right, what we're going to do is we're going to assume that our guess is correct. Well, we have a 10-bit like encrypted command. We don't know which read page or inverted page command we have, but we're going to assume it's read page 0, right? And so we can XOR that with the plain text of the read page 0 command, and that will retrieve the 10 bits of key stream that would be necessary if our guess was correct. When we've sent it and we get back our 32-bit response, which won't be the error response because it'll be a valid read page command of some description, we can take that read page response and assume that's page 0, which we know because it gets given to us like for free in clear at the beginning of the handshake, right? It's the UID. So we can XOR whatever we get back with the UID, and that will give us the next 32 bits of key stream. So we've now got 42 bits of key stream if our guess is correct. And if our guess is incorrect, we've got nonsense, all right? So somehow we need to check if our 42 bits of key stream is correct or not. So what we do is we create a read page 0 command that is 40 bits long. And we do that using that extended command definition that we had earlier, the thing that we were going to attack. So a read page 0 command would be 1100000111 at the very minimum, followed by 11000 followed by 00011, etc. And over and over and over again, up until the point where you stop sending these blocks. So we can make a 40-bit version of this read page 0 command with extreme integrity, right? And then all we do is XOR that with the first 40 bits of the key stream that we think we've generated to create an encrypted version of that command. And then we send it, well, we reinitialize the tag with the nonce back to the same point again, so it's using the same key stream, and then we send that encrypted read page 0 command, and we either get back the error response, which means that when it decrypted, the integrity failed, which means that we weren't correct, that wasn't the right command, or we get back a 32-bit response, which isn't the error response, which is essentially the encryption of page 0, UID. That means at that point that the first 40 bits of key stream must be correct, and then we can take the response and XOR it with the UID to get back the next 32 bits of key stream, which basically gives us 72 bits of key stream that we know from the point that the PRNG was initialized, from the nonce being transmitted and it completing the handshake, which means that we can send that nonce and challenge response value encrypted and know the pad that the commands and the responses are being XORed with, which means we can do things like this, where we can basically read each page of the tag one by initializing the tag back to the same point, and then do a different read page command each time. And the way we do the read page command is we create the plain text version, XOR it with the first 10 bits of key stream, send that to the tag, and whatever comes back, we XOR that with the next 32 bits of key stream to get back the actual answer, which means that we can then recover all 8 pages of the tag, and 3 of those pages involve the secrets that we need to know in order to be able to talk to any other tag in the system. So it's kind of I think it's a really cool attack. So I implemented it, and the way I implemented it was I took our fiddler made by Aperture Labs, which, if you don't know, is Major Malfunction and Zach Franken, and they've made a really nice bit of equipment. So if you have a Proxmark, which can do low frequency and high frequency, what you'll find is that high frequency is really good, like it actually works, mainly because Major Malfunction wrote the code for that. But when it comes to low frequency stuff, it's not very good at all. It keeps crashing, especially on HiTag2. It doesn't really work very well. However, they made the R Fiddler to kind of plug that gap and wrote the code for it, and it's really good. So I went to the R Fiddler GitHub page, and they say you can download the IDE that you need in order to edit the firmware, and you can download all of the firmware from the GitHub. And then you can start writing your own C, which is just straightforward C. You can read through the code and kind of go, actually, this is quite understandable. It's just programming, like you expect, normal kind of code. And when you actually want to transmit or receive stuff over the RF, you can hunt through the rest of the code base and find out where they've done the same thing that you need to do, and copy and paste their function calls into your code, and then the thing just works. Honestly, it's magic. It did not take me that long. It took me longer to understand the maths in the paper than it did to write the C to actually implement this stuff. So I've added a whole load of commands to R Fiddler. I've extended their sniff PWM command, so I can just literally pull out encrypted nonces and challenge response values. I created a crack command for doing the attack that I've just talked about, a keystream command for the second attack, a reader command so that once you've got the key, you can read any HiTag2 card in that or tag in that system. The clear store tags, count store tags. It's all about weaponizing this kind of stuff, so you can have it hidden away with a battery-powered thing rather than having to carry a laptop around. It's kind of neat. And if you were to do the attack, you'd do something along these lines. But rather than talk about it, let's do a demo. This is the bit that will fail miserably, I might add. But anyway, let's try. Right, so I've got a couple of terminal windows and a whole load of windows underneath you don't need to care about. Right. Okay. So let's... Top tip, if you're talking to EMF camp, don't sit in the sun and drink beer all day. It's not the answer. Right, so this is an RFID, R Fiddler, and I'm already in HiTag2 mode. So I'm going to put that into sniff PWM. I'm going to clear it, and then in store mode, I can't type. Don't worry, I'll worry about that in a second. I just set up another one over here. So I'm going to create one as a reader. That's the one that I've just I'm hoping to configure there is going to be the eavesdropper. It's really funny trying to type one-handed, but it's okay. Honestly, we have trust. I can tell we have faith in the room. This will all be super marvelous. Right. Okay. So I've got a fake reader set up. So if we come back to this one, we want to sniff PWM store. Okay, so you can see the start auth commands. The reader is constantly emanating start auth using pulse width modulation mode of modulation over the field, right? That means that it's shouting out start auth, start auth, start auth, start auth, because it's looking for a tag. many, many, many times a second. So I'm going to introduce the tag, and I'm hoping we're going to manage to read it. Hang on. There, right. So that is kind of reading it most of the time. And what we're capturing will be the encrypted nonce and encrypted challenge response values, assuming that that's working. All right. So let's stop that. Am I in the right? Yep. Right. So let's see. Oops. Let's see what we've managed to capture. List L. There we go. Right. So we've captured all of these encrypted nonces and challenge response values. Now you see the ones that are FFFFFFFF. Clear, it's an error. Right. Ignore that. There's no guarantee that those will have been received like clearly, right? But we'll just trust that it's the case for the time being. So if I now take, hang on, I take the one that's the fake reader out of the way, and I just have this R fiddler here and the tag. Now what I'm going to do is place the tag on the antenna, and I'm going to try and crack it using one of those values, right? So, where's my cursor? I can take the last one if you like. I can take the first one of this page if you like. I could take any in between apart from the FFFFs. Does someone want to shout stop, and I'll just pick one at random? Yeah? That one there. We shall have that pair, okay? Now, as a magician, clearly I will have forced you to the only one that works in this list. But honestly, we'll come back and try it again in a minute with a different one, just to prove that I'm not using magic and mind control to trick this. Right, so what I'm doing is I'm going to run the crack command with this particular encrypted nonce and this particular encrypted challenge response value that goes with that nonce, right? It will get the UID off the tag itself. It will hunt for a valid read page command. It will then bit flip and try each of them out until it finds a read page 0 command, and then from there it will read the whole of the tag's banks of memory, right? The reason I tell you this before I push enter is that when I tested this in my demo, I pushed enter and it just happened immediately, and people weren't convinced that this was actually doing magic. So, brilliant. Cannot get UI. Oh, okay, right. I just need to move. It's all very. See, this is the trouble with like things that aren't software. It's very, very sensitive. Right. Let's try that again. It's such a big build-up for such a big error. Hang on a moment. Hang on. God, where's InfoSec Westwood to like take the piss? Oh God, for fuck's sake, man. Don't keep that bit on the film, will you? Because, yeah. You're in the same window as the reader that you moved out of the way. I'm not, surely. No, this should definitely be 1411. That should be 1421 down there. That one's still reading, in fairness. Honestly, that one is still reading. I know you're being helpful. Oh, for fuck's sake. It's like not having two hands. It really is like this is accessibility errors. Yes. Or I could just hold, you can just hold it there. I mean, I don't even need like two let me just see if I can get a UID off it. Right, hang on. Right. I'll tell you what, let's kill the other one. Right. That one is gone. It is no longer. Right. It'll work now, I guarantee. Analog electronics is so easy. I don't know what you were worried about. Right, so anyway, we need to run this command up here, okay? And honestly, we will come back. If this completes super quick, I'll do it again with another pair so you can see. Oh, look at that. It's actually searching for a read command. It's gone off the side of the page. Ah, it found one. And, God, geez, that's actually a really good demo. But there you go. And so you can see that that is definitely a tag that I've read, because page 4 says dead beef and pages 5 and 6 are my office phone number. Feel free to ring me with all of your HiTag2 woes. But now we know that, we could do things like we could put it into HiTag2 reader mode, and we could use the key that we can pull out of pages 2 and 1. So that is the key, and we run that. We could then take our other tags, which are hidden away down here. See, we don't have to crack the other tags. We can just read them. You see, so that one is beef face. That one is feed face. And if we read the special tag 4, we notice that pages 1 and 2 are inaccessible, because it's been configured to not give you the contents of pages 1 and 2, which I'm now going to flip back to my slides and talk about very briefly. So that was the demo. Tag cloning. If you know the key and they are not protecting the tags, you can just read the tags using that key that is provided. And then once you've read the tag, you can write that to another tag. The UID will be different, but it doesn't matter, because the UID is not used for any access control decisions. It's only used as randomization for the PRNG at the start of the crypto. And you can potentially do that at a distance, although anyone who wants to do it at a distance who knows analog electronics, get in touch. We have money, and we'd like to help write something or build something at a distance that works. So I'll quickly move on to my closing remarks. This attack is amazing. It's really cool, not because it attacks HiTag2 or you could use it to steal cars, but because it's a really neat way of abusing the protocol of the crypto and abusing something that people would generally think was secure to actually retrieve all of the secrets and within the system. So read the paper. It's really clever. Although it is hard to read, but you might want to read the code instead. But if they do protect the tag, then you can't use that attack, because you don't get pages 1 and 2, you don't get the key. That stops you being able to clone tags. So instead, you need to use attacks 2 or 3 that come from the same paper, or attack 4 that comes from the later paper, or 5 that comes from the early GPU attack, or 6 that comes from the later GPU attack. So to put those into context, attack 2 to recover the key takes 2 days to build a table, a minute to get key stream off the tag, you need a valid tag, and then 2 minutes to search the table to find a matching key, right? So if you've got a valid tag, attack 2 is really awesome. If you haven't got a valid tag, you can use attack 3, which only attacks the reader. You need to spend 5 minutes collecting values, but once you've got those values, it takes 16 minutes on average to attack the tag. On my Mac, unoptimized, they reckon they can do it in 6 minutes, hence gone in 360 seconds. 6 minutes, 60 minutes, whatever. I didn't really bother optimizing that attack. But basically, if you can get the values from the reader, you can attack that really quickly and get the key. Equally, attack 4 takes the same values, but you only need about 16 of them, maybe 16 to 32, depending on how many, on your random luck or unluckiness, because it's a fast correlation attack, which is based on probability. And the actual attack only takes 45 seconds. It's really awesome. But you could just take 2 of those pairs of values and run them against attack 5 or 6. Attack 5 would take 2 hours on average on EC2 using a P2 X large. But if you run it against a P2 8X large on Amazon, which has got 8 GPUs, you can get it done in 15 minutes. The same code will work over multiple hosts with multiple GPUs. So you could like halve that if you had 2 hosts. You could quarter if you had 4 hosts, etc. And it all costs the same amount of money, which is $5, which is a very cheap way of attacking someone and stealing someone's BMW. So the point that I'd like to make in my penultimate slide is that we can learn lots from academics in the world of crypto, right? So in the world of like academia, they might not be the best hackers in the world. We might think that we know more than them because we're down and dirty and we're like messing with like tools and attacking networks, and they are theorizing in their ivory towers. But when it comes to crypto, theorizing in ivory towers seems to be the way to get the answers. And I think that when they don't provide the tools, we can take their maths and we can implement it and make our own tools. And that there must be a lot of stuff that we haven't even noticed yet because we are just simply not looking there. So I think we should look more in the world of academia, implement more of their stuff and scare everybody with that. So my final slide is simply the GitHub for Aperture Labs Limited, which is where you can find the RFID RFiddler source, which has got all four of the it's got the first 4 attacks and all of the slides to explain it, and you can find my contacts. You can get in touch if you wish. Thank you very much. I will be drinking more. $42. The mic's not on. Can you turn on the mic for the audience, please? Try talking. It might work. Do you want to just shout and I'll repeat it? Oh. Yeah.
Check.
There you go.
So obviously, string ciphers based on LFSRs are not exactly state of the art, but could we salvage a system like this by taking a page out of the Blu-ray book and having each tag have multiple, say, 64 keys on it, 64 different keys on it? So when you actually steal one of the cards, you can compromise those 64 keys, but somehow, by clever use of the other keys, you are able to still keep the integrity of the entire system.
I think, I mean, I've not looked at that attack. I think adding more keys would just give me more things to attack, and I'd end up with a bank of 64 keys in the dictionary, and then I could probably use that to attack the rest of the system and clone all the tags. What you need is integrity protection, not obfuscating of the keys. So that's what this tag system doesn't provide, and what one-time pads and stream ciphers generally don't provide is integrity. But nowadays we have GCM and various other, authenticated encryption. So, yeah. Go on, Graham. You were going to... No.
No. Okay, you're probably going to have to be the last one when you set up for the next speaker. And I have announcements.
Just a quick question. Would all of that bit flipping have not worked if they'd put like a checksum instead, or CRC, something like that?
No.
It doesn't help at all.
No, it doesn't really solve the problem at all. It's because at that point we have the pad that we're attacking, so it might expand the space that we need to search within, but it wouldn't actually solve the problem.
All right, I think that's all we have time for. Thank you very much, Kev.
Thank you.